Okay, here's the second video on in chapter 4a, and it's basically talking about precipitation reactions. So, first thing I'm gonna do is kind of piggyback on the last one. We're going to talk about two aqueous solutions that we have actually in two different beakers. We have one here and we have one here. And in this one, what I have for a chemical is sodium carbonate. I think we actually used this in one of the labs. And in this beaker, I have something, I'll say it's calcium chloride. Okay. Both of these, and we put them all in a little beaker that has some water in here. And what we find is, for both of these ionic compounds, both of these salts, and by the way, a lot of times you heard the word salt. Salt is kind of a lot of times a shorthand for ionic compounds. Both of these ionic compounds, when put in water, will dissolve freely. And in this case, you'll essentially have sodium ions floating around, and you'll have carbonate ions floating around. And if you remember, carbonate has a double negative, which is why we have two positive sodiums running around there. And of course, it's dissolved in water, and the reason why it dissolves, again from our previous video, is that the water molecules get in and essentially split, divide up the sodium carbonate, so that the sodiums are kind of are separated from the carbonate and are associated with the polar nature of oxygen in water, and the carbonates tend to be associated with the hydrogens. And in fact, you'll even see in a solution like this, you'll see some waters. I'll draw another one here. Hopefully you can see that okay. Yeah. You'll see that even in the water, sometimes one of these H's will even go away. I probably should have drawn this carbonate a little bit bigger. Let me try that. I'm going to expand our beaker here. Okay, and the carbonate again looks like COOO, like that. And these guys are negative. These guys are the negative poles, so they tend to kind of associate with the hydrogens. And what you'll see in some of these in some of these cases is one of the H's will disappear entirely and come over here, and that results in this guy being negatively charged. And now this guy, instead of having a -2 charge, actually has a -1 charge. So again, in water, you'll see this happening all the time, where the hydrogens will come, the hydrogens will come off of water and attach itself to something else that's somewhat negative, and then in an instant go back. And this kind of happens all the time inside solution. But it's that nature of water that allows the solution to be kind of this negative, this polar mix of plus and minus charges rolling around, which is why ionic compounds, a lot of them will freely dissolve in there. And it's just because that the attraction between sodium and the negative bits floating around, whether they be OHs like I've drawn, or just the negative side of a water molecule, they're more attracted to that than they were attracted to the carbonate itself as a solid. Okay, anyway, enough of that. Similar thing whoops, I didn't mean to do that. Similar thing happens over here, where you've got calcium ions, the 2+, floating around with the chloride anions as well. Okay. All right. So, and you can imagine the water kind of doing the same sort of thing over here, but I'll leave that off. All right. Now, what happens if we take these two beakers and we pour them together? We pour one into the other. We actually did this, I think, in a lab. And what you'll end up with, at least for a moment, is a beaker that contains sodiums, chlorides, calciums, and carbonates. And they are, at least for a moment or two, floating around here. in solution. Of course, all mixed in here is water molecules jammed in with its negative and positive charges to kind of keep these charged objects happy, meaning attracted to the opposite charge. All right, now the reaction we're talking about now is the precipitation reaction. What you'll find is, in the same way that we were able to dissolve these solids in water because they would rather be dissolved as ions, rather meaning it's better electrically for them than to be as solids. You'll find that when ions are floating around like this freely, that sometimes the ions actually want to come together and form a solid because the actual attraction, the solids, the bonds that make up the solid are stronger than the attractions happening in solution. And in this case, when we mix these two together, what we find is, and we actually did this experiment, the calcium and the carbonate join together and actually start to form a solid. And at the molecular level, truly this actually happens, is these two form a bond that is just like the bond in a solid lattice of calcium carbonate. And it forms, and it's going to be hard for me to draw the lattice, but it's almost like, well, it's almost like, you know, bricks in a brick building. Is this brick attached to this brick, and immediately another calcium ion floating on there is going to join to it on the along this axis as the crystal is growing, and it just keeps going that way until all the calcium and carbonate, or almost all of it, are taken out of solution. They're no longer ions, and instead, down at the bottom of your beaker is a little bit of calcium carbonate as a solid. Okay. And it's kind of a milky white thing, and you'll see when we pour this together, immediately you start seeing, you know, kind of a cloudy white solid forming inside your beaker. And essentially, it forms because calcium carbonate, as a compound, would much rather act as a solid than as a dissolved mixture of its ions, at least in water. Now, it's very possible that if we actually added calcium carbonate to a different liquid, not water, but to some other liquid, that it may actually find that it wants to split apart again. And that's what you'll find. And this chapter, and a lot of times, a lot of books focus on water as the most common solvent because it's so prevalent in our experience, in the human experience, and certainly in life. But there are other solvents as well that have different characteristics. And what I mean by solvents is liquids that tend to dissolve things. There are other solvents that do a better job at dissolving certain compounds than others. Turns out water does a pretty darn good job of dissolving ionic compounds for the most part. But there are some ionic compounds, and calcium carbonate is an example, that would much rather stay as a solid than to dissolve as a liquid. Now, that's not to say that absolutely every calcium ion and every carbonate ion got together and formed a solid. There still will be some calcium and some carbonate still floating around in solution. And that's because calcium carbonate is somewhat soluble. Soluble meaning it dissolves a little bit when put in water. It just doesn't dissolve very much. So it's kind of considered an insoluble salt with respect to water, even though it dissolves a little bit. And you'll find all solids dissolve a little bit in a solvent. It's just that sometimes that little bit is down into the 10 to the minus 15th kind of level, meaning very 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 little of it actually dissolves. And that's the case of calcium carbonate. Now, there's a really and so precipitation reactions are essentially ions coming out of solution and joining together to form a solid. Now, there's a really interesting table because here's a question to say, well, just looking at this, how do we know that sodium carbonate is soluble in water and calcium chloride is soluble in water, but calcium carbonate is not? Is there any rule? How do you know? Do you just have to memorize that, or is there some rules of thumb? There's a really good table, and it's almost worth memorizing, or at least studying to the point where you kind of memorize it. In my book, it's table 4.1, and it kind of covers rules for solubility, and it kind of breaks down like this: that to kind of put the rules in a nutshell, it basically says that 1A compounds are soluble, meaning sodium and something else is going to be soluble, sodium being a 1A compound. Okay. Similarly, ammonium compounds are also pretty soluble. It also says a compound that has nitrite, what else? Acetate and perchlorate. Anyway, now I've decided this is probably a bad thing for me to draw on the board. But it basically says, generally speaking, there are certain compounds that have a cation, and if it has that cation, it's probably going to be soluble. If it has, similarly, if it has a certain anion, it's probably going to be soluble also. The table goes on to say that for some compounds, though, if it has an anion like chloride or iodide, it's probably going to be soluble unless it's mixed with, and then they list a few of the metals like silver and lead and things like that. Okay, and then later in the table it says these other the existence of these other cations or anions are probably going to be insoluble with other exceptions, with certain other exceptions. So it's worth studying that a little bit just to kind of get familiar with. Gee, when you mix 2 beakers full of something, is there going to be a solid that forms or not? And what you look for are pairs of ions that would make up a compound that's insoluble in water. Okay, that's it for this one.